We have seen several classifiers. Now, what we are going to see is we are going to see how to use the metrics to identify the accuracies. Right? We are going to see various visualization metrics starting from ROC curve. Right? ROC full form you already know that receiver operating characteristics curve. Right? I'll put it here. It is receiver operating characteristic curve. Let us learn this ROC curve through some logistic regression kind of plot. Not only for logit, I am going to statically show you by using the SVM algorithm we dealt in the previous class, the practical. I'm going to show you practically how ROC will come in there. And we will understand clearly how to interpret an ROC chart by using the machine learning part. Right? So we can actually understand if anyone give you some ROC plot, how to interpret that whether it is good or bad, or how to identify values from that ROC curve. Right? That is what we are going to see in today's class. Subsequently, we'll be seeing how precision and recall curve can be used, and so on. Then we will be going into F1 score and so on. Right? So this is the thing. Now let us start with a problem statement that I'm having some rat, and this rat need to be checked to be either obese or not obese. A binary classifier task, whether the task rat is obese or rat is not obese. That is what we need to check. So there are some data which says that it is going to obese, and there is some data which says that it is not going to be obese. So what we'll be actually doing, we'll be training the data by using some machine learning model for classifiers. I'll take a logistic classifier and train here. So when I train it using a logistic classifier, I found that yes, this I can plot a sigmoid curve over here by using some threshold value, and based on that threshold, I can classify a particular mouse as obese and particular mouse as not obese. I'll surely have some errors. My errors may say that a particular mouse which is not obese can be said as obese, and particular mouse which is obese can be said as not obese. So those kind of errors can also appear. So now we need to understand why we need to come out of the accuracy and measure some other thing like ROC. So far in machine learning algorithms, we'll be seeing that yes, we got 80% accuracy, we have 90% accuracy, and so on. But it is more than accuracy. We need to understand something else. Now I'll ask you some question. I want you guys to answer for that. If a machine is there to predict a particular person is having corona or not, right? It's like that machine is there, how you will rate a particular true positive rate and a true negative rate. I'll explain what is true positive again. So what is true positive in the sense, if a person originally has corona and the test says that he is positive, that is I say true positive. So we have this on one side, that is a person has the disease and the machine also says that yes, he has the disease. This is on one side. And other side, if the person has a disease but the machine says it as negative, right? Now my accuracy says that this is how many times it is correctly classified, how many times it is wrongly classified. It will take an overall thing and it will be giving me an accuracy result. Now the thing is, whether I'm asking you a question, if a person who is having corona is predicted as positive and a person who is not having corona is predicted as positive, which is more vulnerable? I'll say, I'll draw over here. If a person is there, he is having corona, but he is treated as negative, right? Whether it is good or bad sign, even though a number is very small, the person is originally having corona, but he is predicted as not having, right? So whether it is good or bad,
Bad, sir.
really bad, right? But when you go for accuracy, these kind of things cannot be measured. It will just calculate true positive plus true negative divided by true positive plus true negative plus false positive divided plus false negative. Overall calculation it will say, and it will not give any weightage for this true negatives and false positives. So because a person who is having corona should be is said as not having, and the person who is not having corona is said as positive. So we need to understand that and give weightage for the true positive as well as true negative and false negative. So let us understand how it is can be done by using the ROC curve, right? Now we have trained this particular data by using the logit plot. Now let us see how the variation is going to happen. Now if you see here, and this is my axis where starting from 0 to 1 threshold is there, and we say that it is going to a particular higher probability and says that a mouse is obese. I have covered all the probabilities. When it is zero, closer to zero, it means that it is not going to be obese. And when the probability is closer to one, it is confirmly saying that it is going to be obese. So that is what we actually have here. Now let us assume a mouse is over here, right? I have several kind of mouse here. So the red color actually means that not obese. Blue color actually means that obese. So I have a test data. So this is after training my model, I have plotted something, and this is the test data that comes into play. And for this test data, I have to identify what is my accuracies. Now let us see how the plot actually looks. See, this plot is correctly classified. So the red ones are correctly classified red, but this is wrong. So if you see here, this plot is actually wrongly classified, and this is also, it is actually red, but it is classified in blue position, right? So this is wrong and this is wrong. So it is not that we are having three actually correct here and three actually correct here. We need not want even this to even this to appear and even this to appear. This is wrongly classified and this is wrongly classified, the test data. So we need to cleanly understand what will be the nuances when we wrongly classify these kind of data also. So let us see what and all will be the troubles if we wrongly classify these data. By confusion matrix, we can do that. For example, in the confusion matrix, we say this is true positive, where the mouse is actually obese and correctly predicted as obese also. So three of them, which is actually obese and correctly predicted as obese also. So good, no issue is there. But when a mouse is actually not obese, but it is predicted as obese, this is actually not obese, but it is predicted as obese. So this is actually the first problem. That is, it is actually not obese, but predicted as obese. Second, this is actually the thing where it is not obese and correctly predicted as not obese. So no issue with this. And but here, it is actually obese, but predicted as not obese. So this is with respect to the rat, but within the same situation is going with respect to a very big disease like corona. Then these two things also should be given some sufficient weightage. Now we need to understand which is actually a strongest among these two. Whether this error is strong or this error is strong, we need to identify. When someone is actually not obese and you say that it is obese, that is when someone is not having corona, but you say it's corona. But after some time, he may go to the clinic again and we can test it again. No issue will be there. But if a person who is having corona, but your machine says it is not having corona, then what will it happen? The person will survive as it is inside the environment, and he will make more things to happen, more corona to be spread. So compared to when you say it is not having corona, but you say corona, it is actually somewhat more sensitive. It is sensitivity. But here, when you say that a person having corona is not corona, then this is more dangerous. So I need to give more weightage to reduce this false errors. So the false errors I need to reduce. So that is what the thing I'm going to do. Overall, if you see, the accuracy will be same when I change these or these things. But I don't want this kind of error to happen. So when you say that one particular error, like false negative, after this false positive error should be reduced, or true negative error should be reduced, then you need to go for some other visualization curves like ROC. Right now, you see here, we'll start with using some threshold. By using this threshold, we classify all the samples as obese. I don't treat any samples as not obese. I treat all the samples as obese. Then what actually happens is, if you see here, I have all the if it is actually obese and the prediction is also obese, I have four things correctly classified. And if four not obese and this is also not obese, then I can say that it is very good. Why? Because there is nothing like when it is obese, it is not saying not obese. So like that, I'm not gay. So I'm just changing the threshold of the logistic regression. You know, right? When I move the sigmoid curve, if I vary the threshold, then my values also will vary. Right now, I vary the threshold. When I vary the threshold and see, I found that this true positive is actually good. 100 percentage, if it is obese, it is correctly predicting as obese. And when it is not obese also, it is saying obese only. It means that whatever data you give, I will be saying as it is obese only. I will not say any other things, right? So if you do like this, then what will happen? Now you calculate the true positive rate, also called as sensitivity. So how to calculate the true positive rate is you take the true positive divided by true positive plus true, that is false positive. True positive divided by true positive plus false positive. Then if you take the true positive rate, you'll be getting as 1. So this is what says that your sensitivity is 1. Why? Because whatever data you give, you actually give it as the same value, obese. Right? So this is the curve. And you calculate the false positive rate, also called as 1 minus specificity. To take this, that is false negative divided by false positive divided by false positive plus false negative. This is false positive, that is it is recognizing the positive data as false. So false positive divided by false positive plus false negative. So again I'll get as 100%. Right, now if you plot the curve and the ROC for the threshold equal 1, because it is 100% says the same result. For the threshold equals 1, the ROC curve will plot the true positive and false positive rate as here. According to the ROC interpretation, if your plot lies to the top right position, then your model is actually predicting in the worst. It is very worst. It should never, it means that the model is not working itself. For whatever data you give, it gives the same answer. So ROC curve should not be in the top right corner. If the ROC curve is towards the top left corner, it means that your model is doing a very good job. If it is in the top left corner, but here it is in the top rightmost corner, so it means that the model is performing worst. When it will perform worst? When it is giving the same answer for all the variations you give for all the classes. So what I will do, I will try to change the false positive rate. True positive remains the same. I will try to change the false positive rate, where here the false positive is 3 and the false negative is 1. So I change it. Now if you see, it is actually 0.75 in the true positive thing and 0.75 to 1. So my value is actually decreased because my false positive rate is decreased to 0.75. So what happens? I should not wrongly predict a particular answer, right? So what happens? My ROC curve is actually moved to left this time. So I further increase this, then I increase the threshold. So what happens? My ROC curve will move even more left. So ultimately, what I should repeatedly do, I should try to reduce the sensitivity and specificity in such a way that it should be on the leftmost corner, where my false positive rate should be closer to 0 and true positive rate should be closer to 100. False positive rate should be small and true positive rate should be largest. I should be doing like that. And this is the original confusion matrix what we actually dealt. And for this, if you see, it is 0 to 0.75. So I mean that I have reduced the false positive rate throughout to 0 and true positive rate to 75%. Means that 75% it correctly classifies the positive data as positive. If the person is obese, it will 75% correctly classifies as obese, right? But in the negative end, it will not do any negative. 100%, if it is not obese, it will say as not obese. So that is over here. So when it is in the top leftmost corner, so I can not top leftmost is over here, but I'm not able to get it. You can get it in very rarest sense where true positive rate is 100% and false positive rate is 0%. If the case is like that, then you can get a curve over here, your point over here. Now, so if you further increase the threshold, then what happens? After a particular limit, it cannot move further. Your true positive also will come to reduce. And up to a particular limit, what happens? Both true positive and false positive becomes 0. And this is means that the model is actually beyond some threshold and it gives only 0. Right? Here where the ROC curve actually ends. So from 1, 1, where the false positive rate is also highest and true positive rate is also highest, and that is the very worst case. And 0, 0, where false positive is also 0, true positive also 0. This is also the worst case. So this line is actually the line which actually separates the accuracy. It should not be either 0, 0 also. It should not be either 1, 1 also. How it should be? A very good ROC plot should have 0, 1. That is false positive should be 0 and true positive should be 1. So this is actually the very good plot. But having this is actually mean that 100% accuracy is there, but that is not possible. So we can actually identify. So then what is my best plot here? My best plot can be something over this. I can have my best plot as this is my best plot, or I can actually change it between either this or this. So I can have either this or having this. So if I want to have some false positive rates, if I don't want to have a very good accuracy, then it may result to overfitting also. So I can select this or this or this. This is actually very worst. So I will not select this. I can actually go on with between this or this. Anyone I can select, and this the particular threshold I'll fix. So ultimately, what is ROC curve is when you vary the threshold for classification, you will have several different true positive rate and false positive rate. Ultimately, what you have to do, you should reduce the false positive rate as much you can. So the false positive rate should at one time should become 0, and true positive rate at one time should become 1. So that is what the best ROC curve, but that is actually not possible. So what you can do for me for this particular model, the ROC curve for different threshold will be like this. So ultimately, if I want to draw the ROC plot for this ROC plot goes like this. This is the ROC plot for the given model, right? And this area that separate the main line to this is what the area of ROC. Now let us see how the area actually behaves. Right, the area I will call it as area under curve. Right, now if you see, I have two ROC curve. This is one ROC curve, say model 1 ROC curve in red, and this blue represents model 2 ROC curve. So when I need to compare the two ROC curves, then I can use something called as AUC. So what AUC actually means, AUC represent the area under the curve for with respect to two ROC curve, right? The area under curve says that it should be as large. Why? Because if it was actually closer to 0 comma 1, it means that the area under the curve will be 100 percentage. So entire area will be there. If it was falling down, then the area will actually reduce. So compared to red and blue, if you see, the red is actually somewhat good. Why? Because it has more area, where blue is having only less area. Ultimate best one will be this particular curve. This will be the ultimate best, where 100 percentage all the area will be 1. If you have any ROC curve like this, then it means that your model is performing a very good job, right? This is with respect to the ROC curve and the AOC curve, right? Now I'll give a quick recap so that you can understand both. So let us, I change the pen. Let's see what is ROC. Receiver operating characteristic, right? First one, it is actually the way I'll use a paint window, that will be better. Is a receiver operating characteristics ROC curve, right? The main point is ROC plots true positive versus false positive. Right? This is actually the main point. ROC actually plots true positive versus false positive. Now, what is actually true positive? True positive says me, if you go and see here, true positive says me true positive divided by true positive plus false negative. So this is actually the case over, right? When if what is a comparison over the accuracy plot is, when I say accuracy of a particular machine learning model is around 96 percentage, then it means that it can either be like true positive will be higher, or false positive and true negative may be lower. So which is actually lower, I cannot actually judge. So I need some variation on understanding what is the true positive rate and the false positive rate. Let us see the formula for true positive. So what is true positive is true positive divided by true positive plus false negative. So this is actually the formula for true positive. So this true positive are also called as sensitivity of a particular graph. This true positive is otherwise also called as sensitivity of the particular graph. Also called as sensitivity Why we call sensitivity is it is as sensitive as possible in the sense whatever you graph you give, I'll be giving some same result if you make true positive higher. So it should not give any small results. Main thing for to focus on the particular machine learning model is if I give anything, how correctly you classify my positive result. That actually says in true positive rate. But false positive, it is actually wrongly classifying a positive sample. That is actually called as false positive rate. Let us see the formula for false positive. Just a minute. So false positive will be given as false positive divided by false positive plus true negative. So this is actually called as the false positive rate, right? So we need to compare these true positive as well as the false positive and give the ROC curve plot. The thing over here is if the ROC curve is in the top left corner, leftmost corner, then the model is good with that corresponding threshold, a corresponding classification threshold, right? So ultimately, what will happen? ROC gives the TP versus FP values for various different thresholds. So ultimately, for the threshold, which is actually in the top leftmost corner, you take and say that is actually the best threshold for the given model. So we know, right, when we actually keep threshold as 0.5 for logistic regression and classify. And if you want to correctly choose a threshold, then the better thing is you have to use a ROC curve. And this ROC curve will say you what is the efficient threshold for the model to do correct classification. Right? This is with respect to ROC plot. Right? I am making it clear on the ROC plot. I'll say one more time also. It will be very useful for your MCQs also. So I'll say one more time with respect to ROC. ROC actually plots true positive as well as false positive. And what is true positive is nothing but true positive divide true positive plus false negative. And false positive is false positive divide false positive plus true negative. So when the ROC curve is in the top leftmost corner, I say the model is good and with the respect to the corresponding threshold. And this ROC, it will give the particular plot for every different threshold that is possibly possible threshold for that particular model, right? Am I making it clear the ROC curve? Shall we go into the practical and see for the SVM plot what we seen yesterday? Yes, am I making it clear? Students? Yes, am I making it clear? Am I audible?
Yes, sir.
Yes. Right, now let us go into the practical case. I'll open that. Yes, I reconnected. I have done the ROC curve and kept here. Yes, I have also done the precision recall. Once ROC is done, I'll teach you the precision recall also. So let us see here the ROC curve. This is actually the simple the code. I have written it as a function here. So whenever you want to use ROC curve for any different any algorithm you want, you can just call this function and you can use. So what is that is I import a scalar and a matrix. Next I import define an ROC curve function which takes y test and y predict. So both values it take and it calculates the ROC curve parameters. So we know that ROC curve takes false positive rate, true positive rate and the threshold. These three things it is required to do the ROC plotting, right? When I want to plot, I require FP false positive rate FPR, true positive rate TPR, and the threshold, right? Next, these three things I can obtain from this matrix.roc underscore curve function with the respect to the y test and y predicted values. Next, I calculate the ROC area under curve value by using the false positive rate and the true positive rate. I can calculate the area under curve. Then I plot it. How I plot is I give the false positive rate as x-axis, true positive rate as y-axis with the B plot, and the label is equal to AUC with the ROC curve values. What is the result of the area under curve also I give, right? Then I also give it this particular labels under will be present in the lower right in the legend, and I fix the x limit as 0 to 1, y limit as 0 to 1, and x label as false positive rate, y label as true positive rate. If you come and see here, yes, this is actually the ROC curve. So if you see here, the ROC curve for SV1, the model SV1, if you see, the SV1 model is over here, which is having an average accuracy of around 60 percentage accuracy it is showing for the support vector machines SV1 model. For SV1 model, the accuracy is around 60, and if you see the ROC curve with me, it clearly shows that the model is not good, right? The area under curve is only 50 percentage around. These remaining 50 percentage it didn't cover itself. So we clearly by the ROC, though we have accuracy of around 60 percentage, this ROC curve clearly shows that it is highly giving some false results. 50 percentage it is giving false result, and see here almost it is in the top rightmost corner. So sure, immediately what I can say that this ROC curve is not good in any for all the thresholds you see, it is not going to the right side. True positive rate and false positive rate are almost equal. So this curve you see, true positive and false positive are almost equal only. So similar ROC curve I plot for the kernel is equal to a polynomial degree 10. So if you see the ROC curve for this, yes, the ROC is somewhat better here. That is only better in the sense it is actually reduced to 0.8 with here true positive around some 0.9. So for this threshold it is better, and if I decrease over here, I can either take 0.7 to 0.8 I can take, or I can take 0.8 to 0.9. So any one I can actually take and plot. I get the area under curve as actually 57%, better than the linear kernel SVM. So it is ultimately what I have to do. I want this curve to be in as right as possible over here. Around to 0.6 to 1, I should have this curve to fit here. Then only I can say that ROC curve is actually giving me a good result. It is actually denoting some good result. If you see over here for the RBF kernel, for this also it is not that much better. It is actually around this, and this is actually 0.9. It is not 0.8 also. False positive is even more higher to be 0.9, and area under the curve is only 55. Very good area is around at least some 75 percentage should be in the bottom. Then only the area under curve is good. 55 is very low. And if you see for the sigmoid curve is also performing the same worst thing. It is not giving me a better ROS. So we need to operate on the hyperparameters like Yukendra did last class. You need to operate on the hyperparameters and change. The difference between seeing the accuracy and seeing the ROC plot is accuracy combines all the true positive, true negative, false positive, and false negative. But this actually combines true positive and false positive alone and says as some good result. Right? There is another curve called as precision recall curve, which will give us the difference with respect to true negative also. So many different visualization algorithms in the metrics are actually available that will help us understand how good the model is with respect to correctly predicting positive as positive, negative as negative. Right? Everything it correctly says us and visualizes it. But the accuracy is actually the overall term, so that alone will not help us. So only we go for something called as F1 score, which says which parameter is very good. That is given by F1. This ROC says with respect to true positive and false positive. Then we'll be seeing about the precision and recall. That will say with respect to true negative also. So everything we will be actually seeing out, right? So this is with respect to the code. Now I want you to have this code for ROC. Yes. So this is actually the code I have created like a function. So this function you can, without any changes, you can use it for any machine learning models you use. Any classification algorithm you use for a binary classifier, you can use this and you can get the result, right? So that it will correctly say you how the true positive and false positive are fitted. Just to call ROC curve with your test values of test output values and predicted output values. You give their parameters. This particular function will give the result, right?